Reporting from the Arctic shoreline of the Bering Strait. The strong winds and freezing temperatures are a constant reminder of the harsh yet critical environment we are
For a century, this gap between Russia and America was deemed impossible to bridge due to lethal Arctic conditions. Today, TechGen Manufacturing deconstructs the blueprint of a $100 billion spine designed to conquer the -60-degree abyss. The mission: anchor 10 million tons of specialized alloy into the permafrost, surviving pressures that crush standard naval vessels. It begins with the foundation. We are deploying gravity-based caissons, massive concrete fortresses weighing 150,000 tons. These monoliths are cast in specialized coastal dry docks, then towed through ice-choked waters by heavy-duty ice-breaking tugboats. Submerging these giants requires surgical precision. GPS-guided ballast systems lower the caissons to a depth of 50 meters. The tolerance for error is non-existent. A deviation of 15 millimeters would cause structural failure under shifting tectonic stress. Once positioned, high-pressure grout injection systems lock the base into the ancient volcanic bedrock, creating an unbreakable seal. At the waterline, the pier takes a radical shape, an inverted cone engineered to deflect multi-million-ton ice flows. When icebergs collide, the geometry forces the ice upward, shattering the frozen mass before kinetic energy reaches the core. But the real secret lies within the material itself. We are using bio-enhanced, self-healing concrete for the external shell. Billions of specialized bacillus spores are embedded in the matrix, lying dormant until the first micro-crack appears. As seawater enters a fracture, the bacteria activate, producing limestone to seal the gap and protect the steel reinforcement. This living armor ensures the bridge remains structurally sound for a century, even in the planet's most hostile environment. With the foundations anchored, our focus shifts to the bridge's superstructure and the metallurgy required for survival. Conventional carbon steel is useless here. At -60 degrees, it shatters like glass under the slightest impact. We utilize a specialized nickel-chromium-molybdenum alloy, specifically forged to maintain ductility in extreme cryogenic environments. This alloy allows the entire bridge spine to flex and breathe without snapping under immense Arctic wind loads. The forging process occurs in high-pressure smelting plants, using 80,000-ton hydraulic presses to shape the main joints. This massive pressure eliminates microscopic air pockets, ensuring a molecular density that prevents structural fatigue for decades. Once forged, each component undergoes controlled quenching to lock the crystalline structure of the high-strength steel into place. The assembly moves to the box girder line, where hollow segments are crafted as the bridge's primary defense. These girders feature an aerodynamic, inverted wing profile, using Arctic storms to actually stabilize the structure's downward force. 12 automated robotic welding stations execute 5 kilometers of precision seams on every 300-meter bridge module produced. Real-time laser sensors track the welding arc, detecting deviations smaller than 5 microns during the critical fusion process. Every finished weld is subjected to a deep ultrasonic scan to verify the absolute integrity of the bond. Following verification, the steel is encapsulated in a multi-layered polymer shield to neutralize saltwater corrosion from the spray. A modular logistics system synchronizes production with the unpredictable weather windows of the harsh Bering Strait environment. Massive multi-wheeled crawlers transport the completed spans toward the deepwater docks for their journey to the open sea. At the docks, the 300-meter spans are loaded onto specialized semi-submersible heavy-lift vessels for transit. The loading process is a masterpiece of balance, managed by automated ballast systems to keep the deck perfectly level. Each span is secured with high-tension steel lashings capable of resisting the immense torque generated by open ocean waves. The journey through the icy Bering waters is guided by satellite-linked navigation, avoiding moving ice packs in real time. Upon reaching the installation site, the semi-submersible vessel begins its controlled descent, lowering the deck to water level. Giant hydraulic jacks on the pier heads prepare to receive the span, with alignment lasers scanning for millimetric precision. As the waves swell, the active heave compensation system on the cranes neutralizes vessel motion during the critical lift. The moment of contact is managed by shock-absorbing buffers, preventing kinetic energy from damaging the delicate core interfaces. Once the span is seated, high-strength alloy bolts are driven into the joints by automated torque wrenches for permanent locking. This connection is then sealed with a pressurized epoxy injection, creating an airtight and watertight structural bond. We now focus on the interior of the box girders, where a climate-controlled environment protects the critical utility lines. Inside, massive fiber optic arrays and high-voltage DC power cables are installed using specialized robotic cable-laying crawlers. These cables are suspended on vibration-dampening racks to prevent fatigue caused by the bridge's natural resonance frequencies. Automated sensor nodes are deployed every 50 meters to monitor structural health, temperature, and atmospheric pressure levels. Every data point is transmitted to the central command hub, forming a digital twin of the entire bridge infrastructure. With the internal systems synchronized, we initiate the installation of the high-speed rail vibration dampers. These dampers utilize magnetoheliological fluid, adjusting their stiffness in milliseconds to counteract train inertia. Silent technicians monitor the first calibration tests, ensuring the track alignment remains within a micron's tolerance. On the upper deck, the automated asphalt laying fleet begins the specialized polymer-modified bitumen application. This specific road surface is engineered to remain flexible at -60 degrees, preventing thermal cracking. The paving machines move in a perfect staggered formation, controlled by a local mesh network of industrial AI. Following the pavers, robotic rollers compact the surface, utilizing ultrasonic sensors to verify density and smoothness. We now transition to the bridge's external defense, the automated de-icing and heating grid installation. Graphene-based heating elements are embedded directly into the road surface to prevent black ice formation instantly. Energy for these systems is harvested from undersea tidal turbines, anchored to the bridge's massive pier foundations. Divers in specialized thermal suits conduct the final underwater inspections of the turbine housing units today. No words are exchanged. The complexity of the task requires absolute focus on the mechanical seals and gaskets. Back on the surface, the installation of the aerodynamic wind deflectors along the outer railings begins. These curved carbon fiber panels are designed to break up laminar wind flow, reducing vortex-induced vibrations.
Standing here on the Arctic Circle Bridge, you can feel the sheer power of the wind. But this structure was built to withstand anything.
The focus now shifts to the seismic isolation bearings, the unsung heroes protecting the bridge's spine. These bearings consist of alternating layers of high-grade rubber and steel plates, designed to absorb tectonic shock. Technicians in safety gear calibrate the lateral displacement sensors, ensuring a tolerance of 0.5 millimeters. Every bearing unit is subjected to a vertical load test of 20,000 tons before final installation today. Next, we observe the deployment of the fiber optic structural health monitoring grid across the main suspension cables. These sensors detect minute changes in cable tension, transmitting data to the mainland command center every microsecond. A specialized cable climbing robot crawls along the primary span, inspecting every wire for signs of corrosion or fatigue. No human could perform this inspection in these winds. The robot uses magnetic flux leakage to find internal defects. On the rail deck, the heavy-duty overhead catenary system is being energized for the first high-speed electrical tests. These copper-magnesium contact wires are tensioned to withstand the rhythmic oscillations of trains moving at 300 kilometers. Automatic tensioning devices adjust the wire height in real time, compensating for the bridge's thermal expansion and contraction. We move to the maintenance galleries, where silent teams check the massive backup lithium-ion battery arrays for energy storage. These arrays provide emergency power to the de-icing grid and navigation lights if the tidal turbines ever fail. The fire suppression system is also being pressurized, using a specialized eco-friendly mist that functions at extreme cold. Every nozzle is laser-aimed, part of a redundant safety network that leaves absolutely nothing to chance in this abyss. With the safety systems online, we initiate the final calibration of the bridge's structural thermal monitors. These sensors track the expansion of the steel box girders in real time, adjusting the expansion joints precisely. The bridge must breathe. A thermal shift of 20 degrees translates to nearly 2 meters of total movement. On the service deck, autonomous inspection drones launch from their docking stations for a total exterior scan. Equipped with LiDAR and thermal imaging, these drones map the integrity of the polymer corrosion shield today. Silent technicians in the command center track the flight paths, analyzing high-resolution data for any micro-anomalies. The focus moves to the rail system's electrical substations, buried deep within the reinforced pier structures. Massive dry-type transformers convert high-voltage DC into the stable AC current required for the locomotives. The cooling system for these transformers utilizes a heat exchange loop directly with the freezing Arctic seawater. Deep-sea intake pipes are checked for biofouling by automated cleaning robots, ensuring maximum thermal efficiency. No human presence is required here. The entire energy grid is managed by a decentralized industrial AI. We now transition to the installation of the bridge's primary navigation and early warning radar arrays. These arrays detect incoming icebergs and unauthorized maritime traffic, feeding data into the global maritime net. The radar housing is built from specialized composites, transparent to radio waves but resistant to ice buildup. Every component is a masterpiece of precision engineering, designed to survive the most violent storms on Earth. The focus now shifts to the bridge's emergency life support and pressurized refuge chambers today. These chambers are embedded within the main piers, designed to sustain life for 30 days in isolation. We observe the installation of the oxygen scrubbing systems and independent geothermal power generators here. Silent technicians in heavy thermal gear calibrate the airlock seals, checking for atmospheric leaks. No verbal communication is allowed. The precision of the pressure sensors requires absolute environmental silence. Moving to the exterior, the final layers of the radar-absorbent industrial coating are being applied. This specialized polymer reduces the bridge's electronic signature, preventing interference with local aviation radar. Automated spray arms move along the suspension cables, ensuring a uniform thickness of 5 millimeters. Laser thickness gauges follow the sprayers, transmitting real-time coating density data to the on-site engineers. Next, the installation of the high-intensity LED navigation beacons for maritime traffic is completed. These lights are powered by localized solar thermal film wrapped around the upper pylon structures. The film converts even the weakest Arctic sunlight into electrical energy, stored in supercapacitor banks. We transition to the central rail hub, where the first autonomous cargo locomotives are being staged. These trains utilize superconducting magnetic levitation for low-friction transport across the 82-kilometer span. The induction coils on the track are energized, creating a humming magnetic field that echoes through the steel. The inductive power transfer system is now fully operational, providing wireless energy to the maglev fleet. We monitor the first full-scale cargo pod as it accelerates to 400 kilometers per hour today. The aerodynamic profile of the pod minimizes drag within the bridge's semi-enclosed rail gallery structure. Silent technicians check the cooling manifolds for the superconducting magnets, ensuring zero thermal drift. Every sensor in the network reports a green status as the pod crosses the international date line. This date line represents more than a time zone. It is the bridge between two different worlds. The final stage of the project involves the activation of the Global Logistics AI Command Center. Deep within the pylon foundations, liquid-cooled server racks process millions of transit variables every second. The bridge is now an intelligent entity, capable of self-diagnosing structural fatigue and rerouting power dynamically. External maintenance robots perform a final sweep of the expansion joints, clearing the last Arctic frost. The perimeter defense radar confirms that the airspace and sea lanes around the bridge are clear. 99.9% reliability is achieved as the system enters its final pre-launch countdown. This 82-kilometer spine of steel and silicon has finally conquered the impossible Bering Strait abyss. The engineering limits of humanity have been shattered, proving that no environment is beyond our reach.
This incredible structure represents the best of British engineering, finished on time and on budget.